We're so excited to be here today with all of our wonderful students at Pine Grove Elementary in Alabama. Hi, students. So good to see all of you and to have you here with us. My name is Jill Ford. I serve as the Assistant Dean for Student Success at the Klesse College of Engineering and Integrated Design at the University of Texas at San Antonio. And we are just so happy to be in partnership with the D. Howard International Education Foundation on this Rural STEM initiative and to be able to bring this presentation to all of you great kiddos today. Our leader for the D. Howard International Education Foundation, Wayne Fagan, is not able to be with us today, but so I am bringing welcome on behalf of D. Howard and also University of Texas at San Antonio. So happy to have Pine Grove Elementary with us and so happy to have Valerie from Blue Origin with us as well today. And so with that, I'm going to turn it over to Carlos and then we will get started with the presentation.
Thank you, Joe. So just to give everybody an idea of the format for today, so we'll have our lovely presentation here to start. And then for our students in the classroom, if at any point, if y'all have any questions, feel free to put them in the chat. We can either try to answer them for you in the moment, or if not, we'll have a formal Q&A time at the end. So if you do have some questions, or even if you want to write them down or anything, at the end of the presentation, we'll loop back around and answer any questions that either we might have missed or any new questions that you might have. So be thinking of things that you'd like to ask. If you have any things that you'd like to add in or learn about more, we'd love to address and help add into the learning that you have already. And so with that, we'll go ahead and get started. And so today we're joined by Blue Origin, as Joe had mentioned, with Valerie Bouagnon, who's an engineer over and operations training over at Blue Origin. So I'll pass it over to you and you can get us started for today. So thank you.
Hi, everybody. I'm so happy you guys invited me. This is awesome. I do a lot of volunteering with young children for all my life. And I'm super passionate about sharing knowledge that we have to you guys. So, hey, this is me. So I'm an aerospace engineer. I'm also a professor. And if you look at the glasses, you can see a little bit of a rocket there. So that was like one day when the rocket landed back and we took that picture. So I'm going to show you a tiny video and I hope it's going to play and that you guys can hear it. If you cannot, then I'll probably narrate it. But this is just like a little visual of great.
Oh, actually, Valerie, I think we're seeing the PowerPoint presentation. I don't know if you have another thing that you're showing.
Here we go.
How long did we do last time?
So still the PowerPoint. So ours, we're seeing just the like your slideshows.
Do you not see the rocket going off now?
No. We're saying maybe your other screen. So we see the Blue Origin, the benefit of Earth, and then the Club for the Future.
It's not good. All right, so let me share this. Now, do you see this?
Yes, there we go.
All right, let me start it again then. Could you hear the sound?
No sound.
All right, so I'll do the sound myself. There's music right now. And they're saying the human need to explore is deep with everybody. Our ancestor crossed mountain ranges, sailed over the ocean, and sought out the unknown while always looking to the stars. We're curious, and now we're in the place where we can pioneer new horizons. Earth is blue planet, and all its beauty is just our starting place. 4, 3, 2, 1, take off. People are screaming with joy. Big blasting engine sound. 5,000 feet. Detached. And zero gravity. Now is the time to open the promise of space to all and lay the way for generations to come. That's you guys. When our descendants looks to the stars, perhaps small rock canoes and colony floating in open space, they'll remember this time. When they reflect on where it started, they'll remember this place. And when they honor the first explorers, they'll remember that this was a bold step. We are Blue Origin, and this is just the beginning. All right. So Blue Origin is, million of people living and working in space for the benefit of Earth. So that's our mission statement. And we have different groups of things that we do. So we take care, of course, of radically reducing the cost to go to space. So we want to make that public to everybody, so everybody could go to space. That's the idea. So it would be, like now it sounds like almost so far for you guys to do that, but think of it as, hey, I could take my car, I could take a rocket, So to utilize in space resources, so there might be a lot of good things out there for us to use. And so maybe that'd be cool. So like, let's say there's gold somewhere, or maybe we could use that. And then to inspire the next generation. So guess who's the next generation? I could see you guys right there. And we want to make sure that you guys have fun and decide to go up in space as well. So we have a new Shepherd. That's the first project here. We have New Glenn, which is a rocket, bigger. So this little one can actually fit inside the big one. And I'll explain a little bit more about that. We have an engine program, and we'll talk about this. And then we have advanced development. So for example, replacing the space station. So the next generation is like right now, right? I'm talking to you guys, and we want to make sure that you be part of the future, and you can send postcards up into space if you want, and have them fly at Blue Origin. So every astronaut also does the same thing, and they can send a postcard up to space. So you can see here William Shatner, who's the same guy that did Star Trek, and other very famous people that did that thing. All right, so let me talk to you a little bit about me, where I come from, what I am, who I am, and all these things. So I called myself a world citizen. So I generally don't say, hey, I was born in this country, because I lived in so many different countries. I feel like I belong to a lot of places. So I like to call myself a world citizen. I think it's a good appellation if you're working in space and you say, where do you come from? Well, planet Earth over there, right? So imagine if you're traveling from space to space, that'd be kind of cool. A lot of people ask me, hey, how come you became an aerospace engineer? Like, why did you do that? And so when I was itsy bitsy little girl, my first memory as a child was my grandfather waking me up and say, hey, you need to come and see this. This is like a really important day. You have to remember this the rest of your life. And it was like in the middle of the night, and I didn't really understand. And I saw the first man on the moon when I was an itsy bitsy little girl. So that's probably why I wanted to become an astronaut. Say, hey, I want to do the same thing. So in order to become an astronaut or an aerospace engineer or somebody that does that, you need a little bit of studies. So here's some of the studies that I've done. But when you do a lot of studies, you should also have a lot of fun. So I do cool stuff like volunteering for young people, or I do flight testing aircraft, or I create training for companies, and I love to fly hot air balloons. So I have a hot air balloon, and I'm a pilot, so I can go and float above the trees very slowly. So what do I do every day? So we have a lot of positions and a lot of jobs that need to be done, but my specific job is to train astronauts, to train the people that are going to be working in mission control, so the people that fly the rocket. And we also train all the people that maintain the rocket. So because it's a reusable rocket, which is 95% recyclable, when it lands, then we have to go and fix whatever is broken or whatever needs to be replaced, and then it's ready for flight again. And we also need to train all the people that work on the launch pad, because every time you launch, it burns from the fire. And so we have to fix a lot of things, even though we use material that's very, very robust. So you can see a lot of the trainings. And I like to put the picture up there of all the women astronauts that flew with us. So all the young ladies out there, you could see it could happen to anybody. It doesn't mean because you're a lady, you can't do it. All right, so I'm not just one person doing all this. It takes a big team to do a lot of things. And so right here you have the picture of the launch pad and the rocket on the launch pad, and then the landing pad right here with the rocket just landed. You can see it kind of burned a little bit the landing pad, and so it's going to get cleaned up. And you can see in the back the desert, so in case something goes wrong, nobody gets hurt. And then all the team that work on the rocket. So that's kind of like a happy day when you're like, yay, we did it. And then the rocket landed safely, and then you can celebrate. So that's a celebration picture there. So I ask your teacher, I think your teacher is Mrs. Kimberly Norton, I think. And I asked what you guys were studying and also what kind of questions she had. And she was really sweet to send me a lot of questions. And a lot of the questions were around the engine. And so the engines are really, really big because you could see a little man all the way, itsy bitsy bitsy. So this is not just the engine. This is the end of the engine. So it's much, much, much bigger. So I'll try to kick that video in, hopefully. Oopsie. So you could see how big this thing is. So this is a facility where a lot of the engines are made. And check this out. This is steps so you can go up on there. So this is just the nozzle. So you have also all the rest of the engine where all the combustion is happening. So that's just the tip, the end where the fire comes out of. And I'll show you another video in 10 seconds where you can see where the fire comes out of it. So you see how a man is very small compared to it. So it's just the end part is bigger than a man. So the whole thing is enormous. And we're going to have 7 engines on one rocket. So just to propel everything up in the sky. So that needs a lot of force to be able to do that. Notice on the floor, you have a lot of things. You can't step on lines. You have to respect stuff. All the labels to protect employees so they don't get hurt. This is called, it's also a form of nozzle. So it's kind of like this thing, but here it has where the engine is, and it's going to have the exit. So it's like where this part goes right here. So this and this is going to be attached with each other. All right, let me continue this. So you're into that plant right now. Pretty cool, right? All right, so I'm gonna stop that one and go back to our presentation if I can. I hope so. And then continue from where we were. So here we go. I'm gonna show you another video. So this one is mission control. So one of the thing you said is like, hey, how do I know?
Valerie, I don't think we're seeing this video. So I think we're still
hold on.
seeing the warehouse one.
You still seeing the warehouse?
Yeah.
Ooh, not good. Interesting. Let me see how I can do that. It's tricky. We're gonna make it.
Yeah, I think you got it here. It looks like it's changing.
Not good. Good.
It might just be if you like reshare or like stop and then reshare.
Yep, that's what I'm doing. All right, here goes. I think you guys can see it, no?
The mission control?
Nope,
Yeah.
still cannot. All right, so this is mission control. So mission control, you look, all the screens is like, you can control, you have sensors that tell you exactly what's happening, the pressure or the heat, or maybe what's happening. It's also where you're going to go, the trajectory. So this is all the stuff that you want to make sure that you can control something with that. So that's how you control the rocket. So this is like command center. Some of you might have seen movies where they say, hey, Houston, do you have a problem? So we have a problem. So that's the place where you would call it in. Okay. So that was a movie called Apollo 13. So here is the big engine. So I'll show you this engine a little bit. So you can see the nozzle. Do you see, remember the nozzle that we just saw in the plant? Well, that little section is, you know, remember, bigger than a man. And so you have all the rest of the engine. And these 4 poles on top is where you attach it to the rocket. So it's like big bolts are attaching it to the rocket. So when the rocket takes off, that whole thing pushes it. So I'm going to show you a video of the rocket blasting. And I know you can't hear my sound, but imagine really loud sound. I hope you can hear the sound, but I don't know.
I think if you were to
Hold
stop
on.
sharing and then just click the little video with sound, I think it'll pull it up for you if you want.
I will try.
Yeah, oh, well, we see it.
All right, so this is an engine. You see the nozzle right there, and you see all the fire. They put water so it doesn't burn the whole concrete. So that's a test. So we're doing this on a test stand. You could see everything is shaking quite a bit, and all the flame and the fire is kicking out. And so we're making sure that all the engines are working really nicely before we even fly them up into space. So that thing will burn, and then we can maybe make it turn and see if it's turning correctly. So that would be the direction. And now it's like cooling off, and you still could see some of the fluids that are coming out. All right, so I'm going to try to go back to my share presentation. Here we go. I think this is good. Oops, I can't move. All right. So what happens? So this is I kind of like this slide because it tells you a little bit the story of what the rocket does. So first it's on the ground, right? And it's going to take off, and there is a maximum lifting force. And this is called MECO, which is like right where the atmosphere is stopping. So, and it's the Kármán line is 100 kilometers above the Earth. So the atmosphere is kind of stopping right around here, right? And then you're going to have what we call separation. So that's where you separate if you think all this is the engine plus all the fuel, and the people are located in the crew capsule. So 6 astronauts are in here, and during that time, above this line, you have 0 gravity. So we went so far away from the Earth that nothing is holding it down, so it falls on the floor. So when there's 0 gravity, if I was to leave this pen right here, it just floats. It wouldn't go neither up nor down because there's 0 gravity. Nothing pulls it down. Gravity is pulled by Earth, right? So big it pulls everything down to it. And so right there, the astronauts can float, and then gently they're gonna be back on Earth. They need to be back into their seat, and then they need to kind of like they're going to come back down through the sound barriers, and after the sound barriers and back in the atmosphere, the parachute can be open, and then they're going to land. And you saw the video before had a big poof. It's not because it lands really hard, it's because there's actually air that's underneath that blows the, you know, makes it like a hovercraft, so it actually just lands very softly. And then the propulsion module, which is where all the engine is, takes off, and then it comes back down, and the engines are turned back on. The little drag things are deployed, so they open up those little things that slow it down. And then the engine is kind of like put on again, and it lands very nicely on the platform, like you saw a little bit early on in the video as well. So that's what happens in a normal flight. And sometimes we have payloads, and sometimes we have astronauts. Sometimes we have a little bit of both. So this is the launch pad. And so the astronauts go up this way and then through the galley, and they're put inside that little capsule. This is a picture I took early in the morning. We like normally install the rocket around midnight, and then the astronauts are loaded around 6:30 in the morning, and then they take off depending on the weather. And so those are the kind of things. And you can see here, all these lines is to bring all the fuel in. So the cool thing about this rocket, it works on hydrogen and oxygen, and hydrogen and oxygen makes water. So it's not polluting anything. It's not even like dirty like a car. So it's like very cool rocket. And that's a cool thing because we're exploring this thing. And in the future on the moon, you can find oxygen and you can also find hydrogen in the rocks. And that makes it that you can then create your own fuel if you were to go on the moon and you didn't have to carry it. So this is the space station that we have up in above us right now. And one of the big reasons we're doing all this effort is to be able to send and replace the space station. And since Challenger and the space shuttle is no longer there, that was the biggest circumference of something. And so if you're going to put payload, which is satellites or something inside a rocket, you need to have the biggest circle to have the biggest habitat. And you can see here, that's what we're trying to do with this New Glenn rocket. And the new Shepherd rocket on which I'm working is we're trying everything on a small scale, so it doesn't cost you too much. So then we know how to do it on a big scale. So your teacher told me that you guys were working on very cool things. And she said you're working on coordinate planes. So if I could hear you guys, I would say, hey, does somebody know what a coordinate plane is? And tell the rest of the class. I'm going to let you guys do that. So somebody refreshes it. Yeah, go ahead. I see hands up. So how about you talk about it? Just refresh that definition. Awesome. It looks like everybody's super engaged here and that everybody remembers what it is. All right. So you remember you have an X and a Y axis and a Z for the third dimension. Maybe you guys just see the X and the Y in school and you have those graph lines, and then you can say a 2, 3 or something like that, right? And you put a point. So here we use coordinate planes, so the x-axis plane, the y-axis plane, or the z one, so that's the third dimension. So if I was to make a box, you know, I would have my x, y, and z, right? So you have those 3 dimensions. So imagine putting a rocket together. So now I have to put the capsule on top of the rocket, but I have to be very aligned. I can't be a little bit crooked, otherwise everything's going to be off, right? So what if I installed it this way? That wouldn't be good, right? Let me try to come closer to you guys. Or even if I was a little bit off like that, that wouldn't be good. I would have to be exactly right. And also when you're launching, you want to be like perfectly lined up as well with the launch pad. So I have to have everything perfectly aligned. And also I have to have the engine perfectly aligned inside the rocket, so it's not to the side a little bit, because then it would launch the rocket crooked as well. So everything has to be super aligned, like aligned with a laser precise. So we use laser to align everything, so we make sure that the line of alignments are perfectly in that way. And so you can see here the XYZ axis and then how it's organized so that people know, hey, this is the Z side, this is the X side, this is the Y side, and not get confused, and make sure that everything goes really, really cool. Isn't it like a cool application of what you guys are learning? So it's like, wow, do you think it happens for your car as well, that people are lining the wheels very, very well with the car? Who thinks it's happening? Yeah. So alignment is one of the cool application of the coordinate planes that you guys are studying already. So imagine that you guys are on your way to be rocket scientists. You're already learning really hard stuff. Isn't it the coolest thing? All right. So let's look at the next slide. I'm kind of a proud mama too. So I have 3 kids, and I like to share. The reason I like to share about that is because sometimes you should not be afraid to ask a lot of questions. You should not be afraid to explore a lot of things. And I want to give you guys that ability to think about it, to be like, hey, I want to do a lot of things. I want to be a mom or a dad. I want to be somebody that influences other people. And you can do engineering, and you can do a lot of things to help other people be the best of themselves. And so these were my kids way back then, where they weren't in Buzz Aldrin's training suit, because you train in a swimming pool to learn how to do things in space. I also love to do other things. Like I said before, I love flying in my hard air balloon, and you could see me like, kind of floating above water there. And I also like to do paintings and singing. And the last thing, the picture in the middle is called Pongsats. And I wanted to show you guys some Pongsats. So I stand in space, and you can see here that it's way, way, way up in space with my students when I was teaching your grade, Pongsats. And so here are the Pongsats that you see right there on that picture. So I'm going to grab one. And so Pongsat is like a ping pong ball, but it's also a satellite. So the thing that I'm holding in my hand right now is actually flown in space. This thing is on that picture right there. So here it is. It's just a ping pong ball, and inside the ping pong ball, we put things in it. Here it was a battery, and we had a solar panel. We wanted to see if it's in space, does it charge differently than it does on Earth? And then you could see also like all the students of my class put their name on the ping pong balls. And this was the school logo. Oops, I think it fell off, but here's another school logo. So they all signed the little ping pong balls. This one had a watch. And so the watch that went in space went a little bit crazy, and the watch that stayed on Earth didn't. So that made us understand that if you're going to send electronics, you can't have cheap electronics, otherwise it's going to fail. And our watch went completely crazy. It was ringing like at all times and days. Another cool experiment we did was to study what space does on material. So we took two little bouncy balls, and the students colored them. You could see that they did a great job at that. And one of them went on Earth, stayed on Earth, and the other one went in space. And then when it returned back to space, they didn't bounce the same way. So we knew that space did some sort of damage to the bouncy ball. Another experiments we did inside was to put marshmallows and also bubble wrap. So we saw that the bubble wrap expanded, because in space, there's nothing like right here, the air is pressing on your head, and you have things that are holding you to the sides that were no. But in space, there's nothing to hold you back. So it just expands because they want to take space. So things that like balloons, they want to take a lot of space. So we saw that. And then another experiments, we did the seed experiments, but another one, you're going to say, hey, what's that? But inside here, there's a film that we developed to see what kind of rays would go through the film and in which way. And we found like really cool things that made like kind of like twirly things inside. And we're like, oh, this is so cool. So we saw a weird type of rays. And all that, believe it or not, with second graders, third graders, fourth graders, and sixth graders, all the way to university. So this ping pong ball experiment went in all grade levels at different levels of what they know and their knowledge. And that was like a really, really cool time. And I wanted to share that with you because maybe your teacher can do the same project with you guys. All right. So some of the things that I think is important to learn, and that is really cool to know when you become an aerospace engineer. So I think that all by yourself, we're not strong enough. We have to have friends, family, and also teamwork. And being together makes you better. You can think better. You can ask more questions, and you can think of all the possibility, and that makes you more successful. If you think you can do everything by yourself, then maybe you're not going to think of all the things that could happen and forget something, and that could be not so good. Another thing is like to really communicate, to talk to each other and to listen. So maybe you have a great idea, but if I'm not listening, how am I going to hear your idea? And then I'm going to miss the point. So those are the very important things. Learning how to speak very well and learning how to listen very well is super important, because you might make a mistake. And if somebody tells you, hey, I think something's wrong here, and if not listening, then there's something wrong that's actually going to happen. Another thing is a lot of people think they have to be perfect. You have to do everything the right way. And sometimes you think of the right way, but it might not be the real right way. And we think we're going to do very, very well, but maybe your mom or your dad or your teacher or somebody else thinks of another better way. And they're like, oh, I thought I was doing very good, but somebody has a better idea of you doing very good. And so it's kind of interesting that you're always trying to make progress, always trying to learn new things, always trying to ask a lot of stuff so you can become very creative and ask all the right questions. Like being curious is so important so you can become an explorer, right? So those are the kind of things that I wanted to share with you. All right, so this lady here is actually my boss. And she's like Laura Shephard, and you saw her in the video at the beginning. And I wanted to make sure that you guys have plenty of time to ask a lot of questions, because then we can go ahead and explore a couple more of your questions. And I saw quite a bit of them from your teacher. So I'm going to take it away because I want to hear some of your questions first. And let me see if I see the chat here, because I might have cool things. Nope.
Yeah, of course. So yeah, no. So if y'all would like to ask any questions, feel free to put them in the chat, because I know we can't hear y'all through the audio. So if you want to just type any questions in the chat, we'll be happy to take them.
And I think you guys could challenge me, right?
Yeah, see if we can stump her. So yeah, it looks like she's gonna type some stuff.
I'm not sure you see the stuff. You're going to see it, right?
Yeah,
Carlos?
I'll see it. So
Okay,
yeah,
cool.
we got our first question. So how does the rocket float in space?
So everything floats in space. So in space, so Newton's first law that you guys are going to study very soon says that an object at rest wants to stay at rest, and an object in movement wants to stay in movement. So basically, if I put this pen in space, there's nothing that is going to exert a force on it. So it'll stay right there. It'll just stay. That's it. It's not going to move neither up nor down. It'll just stay. Right now, my hand is holding it, and I wish I could make it stay because I'm only on Earth right now. So if I let go, it's going to fall, right? But if I did that in space, it would stay there. So I'm going to try as we're speaking to find one of those videos so you guys could see that. So it's not that it's floating, is there is no force on it. Right now, this pen has a force on it that brings it down, and that's the force of gravity that that is pulling on it. Like right now, the Earth is saying, come to me, and it's coming to the Earth, right? But in space, there is not that force. So if you were to leave it like that, it would just stay like this. Now, if you give it a little push in space, it would continue forever until something stops it. So an object in movement wants to stay in movement unless a force is exerted upon it. So if I was to push that pen a little bit on Earth, just like one little of engine, very, very small, even just blowing with my mouth would make it go forever unless something stopped it. Isn't that cool? So you could travel in space forever, which is exactly what the satellite Voyagers 1 and 2 are doing. They don't have an engine that's fueling them. They just got a little push and they're going on forever and ever and ever and ever and ever. So it's not floating. There's no gravity. There's no forces on it. Does that explain it to you guys? And I'm going to try to find a video of that.
Yeah, and while you pull up that video, I'll pull up our next couple of questions. So I'm going to ask the most recent one first because it's a shorter one. So how much fuel is in the rocket? And then the second part to that, if you run out of fuel in the rocket, how do they get back home? What happens then? While you're in space, of course. Yeah, while you're in space.
So the rocket New Shepherd just goes up, and like you saw, it comes back down, right? So that's all it does. It goes up, it separates. It's a good thing I have this marker, right? And then this goes and floats gently with the parachute. This one shoots back down. So we calculate everything so that it could do that, right? So there's enough fuel. We can't lose the fuel. It's going to stay the right way. So you can't lose any of the fuel. If you went to the moon and, went around the moon and came back and did a longer travel, the same thing. You're going to bring on enough fuel to do and more, just in case something happens. And once you're in space, like I said, you don't use fuel anymore. You shut down the engine. As a matter of fact, you just take off, you shut down the engine. So MECO is where we shut down the engine. MECO means actually the E of MECO is engine cut off. So that's like what it means, right? MECO is like where you cut off the engine. And you saw that on that map earlier on that I showed you. So that's pretty cool too. So here's MECO. This is where you cut off the engine. So we don't use a lot of fuel. So you're going to say, well, what is not a lot of fuel? So it's actually thousands of pounds of oxygen. But the good thing is we have so much oxygen, so it's not so bad. And it's liquid oxygen, so it's actually very cold. And we put it in there. And then we have liquid hydrogen, and we also put that next to each other. And then when they're in the engine chambers, so there's the two lines that come in, there's a little flame there, and it ignites, and all the fuel comes out of the engine. So it's like really cool, very powerful. And if I show you the engine again, I think I have the engine picture. I could show you. So this is the pump that brings the oxygen. This is the pump that brings the hydrogen. And then the combustion chamber is right here. And then all the flame that you see right comes out through the nozzle. And this is like all the electronics to control the engine. Make sense? You guys have good questions, but that's not a hard one. Bring it on.
Yeah. How long does it take to build a rocket?
So it takes a while. The reason it takes a while for us is because we're still inventing. Every time we have the rocket, we make improvements. So because you remember how I said before, we're never perfect. We saw something was not so done. And so we are making improvements, making things better. So because we're relearning how to make things better all the time, it takes a little bit longer. It takes about a year to build a rocket. Ours. Some other programs out there build rockets much faster because now they kind of figure out what they want and how it's working, and they're building a lot of them. So that's called being in production. We're still in prototype phase. So we're like trying to see, is this the right way, or do we want to do it this way, or do we want to do it that way? We're still like thinking a little bit. The program is a little bit behind. That's what it's called. Hasn't reached maturity yet. Good questions. Good questions.
How fast does the rocket travel?
It travels way faster than the speed of sound. So actually, when it takes off, you hear a loud bang. And then when it lands, you hear another loud bang. Because it went way faster than the speed of sound. Actually, it goes close to Mach 2, which is 2 times the speed of sound, which is, a lot, like 2,000 kilometers per hour, kind of ish. Very fast. It takes 11 minutes to do the entire flight. So a few minutes to go up, some time to float, and then a couple minutes to come back down and with a parachute. Takes 11 minutes to do all that. It's very quick. Short trip.
Oh yeah, I think we might have another question.
Let me see if I have some of the questions you guys had.
Yeah, and then how far into space can a rocket go that y'all have?
So a rocket can go as far as it wants because, like I said, once you give it a push, it can go forever, very, very far. That's why we know we can go to Mars. We know we can go to a lot of places because once you're in space and you give it that push, it's going to keep moving. What we want to do is do a fast push, so it goes faster to where it has to go. For example, Mars or even further out. Like right now, we have 2 satellites that are outside our solar system. So that's pretty cool. They travel so far, but it's very, very close in terms of stars. They're so far from being next to the next star. And also it takes the radio signal like 2 months to come back to Earth because they're so far away. And that's a radio wave which travels very slowly compared to a light wave or a sound wave. You know, so it's like much slower to come back.
And then, yeah, so it looks like they liked one of the, or some of these questions. So there's one here. Where does the fire come from when the rocket blasts off?
Now you guys know. Can somebody ask that? Can somebody answer that in the classroom, and we'll have a nod from teacher that says somebody got it right. So, hey, one of you guys, can you answer where does the fire come from on the engine?
Yeah, yeah.
They
She
say
said they
you got it. Oh,
Power-
that's awesome. So it's the hydrogen and the oxygen, and then you have a little igniter, right? And then that blows up. By the way, hydrogen is a transparent fire. So if I had hydrogen fire right now, you would not see it. And when the rocket lands, there is a team of 4 guys that walk with a broom, a straw broom. So they're walking like this, and they say, oh, if the broom takes on fire, that means, oops, stay away. We can't go next to it, the rocket. And if they don't, then you can come closer to the rocket. Isn't it crazy?
That's scary. How are rockets built?
So how a rocket built? So we have a lot of different sections. It's like just like a car, lots of pieces of metal, lots of pieces of pipe that you put together and you assemble, kind of like a big Lego set. You take, you know, the red block and the blue block, and then you put them together with bolts and different ways to attach them. So it's really built like a car. So when your mom and dad come and pick you up, check the car, look at how it's attached together. How are all the parts of my car attached together? And then you'll see that there's sometimes bolts, sometimes snaps, sometimes different kind of things. Go ask them to open the hood and see where is the engine of my car attached? How is it bolted to the car? How does it not fall through? What's going on? The same thing for rockets. Just kind of crazy. The first time I saw that, I was like, don't you guys do it in a better way? And it's really like a washing machine or a sewing machine or your television. I'm like, this is crazy. How do you put this together? But it's exactly the same way. That's the only thing we know as humans. It's to build the way we build, right? You take pieces of metals and pieces of bolts and you put them together and oops, it works, it flies, really?
And then, yeah, another question here. So what type of fuel is needed to power the rocket?
So I know you guys heard that answer twice already. What is it? What do we use for fuel?
She's answering it here.
Yeah, you got it. You got it, guys. Awesome. Good job. So hydrogen and oxygen, which is water, the H and then 2O, right? So the oxygen part is O2 and then the hydrogen is H. And so when you put them together, it literally creates water on the outside. So it just creates a little white cloud as you go up in the sky because it was hot, and it creates a little cloud, and you can follow the rocket with that little cloud. It's actually not polluting anything, which is really, really cool. It's, by the way, the only rocket that knows how to do that. So it's pretty cool to be able to do this kind of thing.
Yeah, see another question too about how big is a rocket? And do you have different sizes actually, or is it mostly just kind of the
So we have 2 sizes of rocket. One of them is, I'll draw it. So one of them is about 100. So that's, oops, my drawing is really bad. Let me make this one better. So New Shepherd kind of looks like this. And this one is about, I think like 100 meters. And then New Glenn is enormous. I can't even draw it on this thing. And you could put the entire New Shepherd in it. So I don't know if you guys could see it. My drawing is maybe not that good. but hopefully you can. Anyways, if I was to compare to my pen again, New Glenn is this big, and I would be New Shepherd is this big, and I would be New Glenn, almost. All right, so pretty big difference. So this is New Glenn size, and this is New Shepherd, and of course it's much longer. So it's the other one is very big, humongous. And this one is like you could put 50 people on top of each other. The New Shepherd, if I pile up 50 adults on top of each other, it would make the size and the height of New Shepherd. So New Glenn is much, much higher, kind of like if you compare my arm to that. So it'd be like huge, much bigger.
All right, yeah. Any other questions from any of
So
our...
New Shepherd has only one engine, and it's a small EDBD engine. I mean, it's very big. You saw it, right? And then New Glenn has much bigger engine, and it's going to have 7 of them. And they have to work together. So imagine I ask some of you, 7 people to jump together. Do you think you're actually going to do it jumping together at the same time? How would you plan and how would you communicate that to each other, that you need to start exactly at the same time? Because if one is jumping too soon, then it's going to make the rocket go like this. Pretty cool, right? Do we have other questions?
Yes, yeah, we got another one here. So how do you guide a rocket to a specific destination?
Okay, very, very cool. So a rocket, I knew I was going to come up with some of these questions. A rocket has really cool thing. It has little jets. So I'm going to make a little rocket, and I'm going to make little jets on the side so you guys could see it. So here we go. So imagine that you have a rocket, right? So this is my rocket, right? I'm making a stubby one, but it has little jets. So the little jets will go a little poof of air that goes this way. So the rocket is going to go that way because an opposite and equal reaction, that's another Newton law. So if I push on something, it's going to move it, right? So if I poof something, the rocket's going to go that way. And so that's how you direct a rocket somewhere in space, with tiny little poofs of air. Pretty cool. And we use like the bad air, things that we don't want anymore outside. So that's how you guide the rocket. Another way is what we call gimbal. So you saw the nozzle, right? The nozzle can move a little bit, so it can go a little bit like this, a little bit. So it can go this way or that way. So that allows the rocket to go that way or that way, the opposite way. So if the engine goes a little bit like this, then the rocket is going to go into the opposite direction. Pretty cool, right? So that's called gimbal. So that's when it's taking off or landing. And the other poofs is when it's up in very far above the earth. I saw another hand go up. Yes. I hope it's a hard question.
Yeah, so we have two questions. So what type of material is used to build the rocket? And then how often do the astronauts go to space?
Okay, so we use different material in different sections. So for example, we use, it's very strange, but we use copper for the nozzle. And because we cool it off inside the nozzle is like a little tube that has fluid, so it doesn't melt. Because normally if you put a penny in the fire, it's just gonna melt. And like, I was really shocked to see, wow, you're using copper for that? And so copper is used there. You use aluminum for a lot of the parts in the rocket, especially the walls and everything. And some places you use titanium, which is a metal that resists heat, and that's where the flame is, inside the combustion chamber, not outside of it, which I was very surprised to see. So we use different materials. Sometimes we used plastic. Sometimes we use those new composite materials. Sometimes we even like print, 3D print parts. Even metal parts are 3D printed, like the nozzles. So we use a lot of different technologies and we use a lot of different material to build the things. And the reason people use different materials because you probably know that aluminum can be broken very fast and another one is really hard. So like sometimes you can take a pen and just, oops, you break it. And other times, like if I wanted to break this plastic thing, I wouldn't be able to, right? It'd be very hard. So when you want something very hard, you use this thing. When you want something very light, you use something else. So you try to find, there's a whole discipline of people that try to find the right material for the right thing. And the same thing would happen, for example, with your chairs or your car. And you could see that your car, hey, the fabric of the seat is one way, and then the outside is another way, and the dashboard is a different way. Just like the mouse that I have right here is going to have different materials in different section, you know, maybe inside is very different than the outside, and you use different materials to build things because of their properties. So it's called properties of material, allows you to make the right choice for the right function that you want that piece to do. So there's so much material on the rocket, a lot of it. It's very heavy.
All right, and then I think we have time for one more that we have here in the chat. So are you going to travel to Kepler 186F?
Ooh,
Yeah.
I don't know. I hope so. Who knows?
Well, actually,
It would take a very, very long time to go. And so we're going to try to make it to Mars, and it'll take 2 years just to go. And it's a one-way trip right now.
oh wow. So okay, well we have one more I'd like. So we'll do one more. So how and why do rockets malfunction? That'll be our
Okay,
next
that's an awesome question. How and why does a car malfunction? So we're human and materials also break. So sometimes, you know, you play with a doll and then, oop, I used it the wrong way. Or you use a little car that you play with and then the wheel comes off, right? So sometimes material break. Sometimes you used it the wrong way. And sometimes the person who built it didn't do the great job. So there's many ways to have a failure. Sometimes it's just a lot of things together. So like we call that multiple circumstances. And so it's like we don't want it to fail. We do everything possible not to fail. But sometimes, sadly, it's just you didn't think of something. And sometimes there are new things that you didn't think about that happen in space, because space is still very unknown. It's still a discovery place. We don't know a lot of things. And maybe the ways the solar rays or other type of rays affect the material and change their properties and affect, and then it fails. Or sometimes you have little particles of dust that go really fast, a tiny, tiny meteorite that actually break. So the space station has a lot of problems like that they have to patch almost all the time.
Cool.
Really cool. You guys were awesome. I'm so happy. You're so cool.
Yeah, and so I'm going to pass it over to Jill to close out. But before we do, any last comments or words for the students that have joined us here today? Valerie.
So my last comment was like, there is no limit. Nothing can stop you to do what your dream is. So go big, think a big dream for yourself. Don't be afraid of all the no's you're gonna get. Anybody, whatever color, whatever size, whatever height, whatever is in your heart, you can do anything you want. So go for it, dream big and go for it.
Well, I want to just say a big thank you again to Valerie and Blue Origin for an absolutely wonderful presentation, and really appreciate your time and sharing all of this good info with our students. And thank you again to Pine Grove Elementary for being our host today, and all the students. We're so happy to have had you here. And now I will just close it out on behalf of University of Texas San Antonio and the D. Howard International Education Foundation. Thank you all.
Bye, everybody.